Hey everybody. So we're gonna jump now into um, one of the big reasons we do calculus, similar to Calc 1, is optimization, right? So there are lots of good reasons to do calculus, but one of the big ones, one of the nice applications is optimizations, right? Finding out where something is the most or the least, a maximum or a minimum. And sometimes there's not always a maximum, but we have these concepts of like local maximums and local minimums. So let's start with reminding ourselves about local maximums and minimums for functions of a single variable. So if I have a function like y equals f of x, right, my function could look like this, right? And even though we can see, let's pretend the function just goes on and on and on, even though we can see it gets, looks as if it's getting larger without bound and smaller without bound, we still have this concept of a local minimum and a local maximum, right? And the idea is that you have a point here, right? Let's just put in an x-axis. If you have a point here, let's say it's A, we would say A is there's a local minimum at A if f of A is greater than or equal to f of x. And we use this idea near A, right? And similar, let's call this B, we say f of B is, oops, sorry, I wrote that one the wrong way. F of A is supposed to be less than or equal to, it's our local minimum. Oops. Less than or equal to, and f of B is greater than or equal to f of x near B, right? Well, what we mean by that word near, right, those are kind of problematic words, is it just means in some interval around it, right? So for instance, I haven't drawn the intervals. Let's just focus on one of them. I'll just look at, let's look at A right now being a local minimum. It appears that f of A is the smallest value until we get all the way out about here. So we can make an interval, right? And whatever happens with the function over there, I'll just put the interval there. On that interval, f of A is the smallest value. Now, outside of that interval, we find values that are even smaller, right? So near just means on some open interval, right? Well, we're going to have a similar idea now. So let's start with the definition for local max and mins for functions of several variables, and then get a picture of the sort of comparable idea when we've added a variable. So we will say a function, let's say z equals f of xy, has a local max at the point AB if f of xy is, let's see, we're doing a max, so less than or equal to f of AB when xy is near AB, okay? And again, we see this word near show up, right? It can't mean the same thing it meant for a single variable because we don't have the same notion of intervals for single variables, right? We've got a more complicated picture. So we're going to come back to that near in just a moment. Let's finish this definition. We say the number f of AB is the local max value, right? So we'll say it has a local max at, and we give the input, just like in single variable, we say at the x value, right? Here we're putting at the input value. And then we'll have a similar definition. We'll say f of xy has a local min at AB if the values of the function are greater than the values here when we're near there. Again, we have to define what we mean by near. And the same thing we call f of AB the local min value in this case. Okay, so here's what we mean by near. Near now, instead of an open interval, near is a disk centered at AB. Right, so here's the idea. If you have a surface, so let's say I have some surface, right? Let's try to draw, maybe it's got a little hill in the middle of it, right? And maybe the surface gets larger and larger over here. I'm just going to end the drawing over here, but maybe it gets larger and larger. It doesn't matter because this point, let's put a point in right here, right, is above all the points nearby it, right? And near now means if we go down to the XY plane, let's say here, so if this is the point, maybe I need a darker color. Let's say this is the point A, B, f of AB. Then if we look down in the XY plane at the point A, B, 0, that we could draw a circle, a disk around this point, and any output in this circle will be less than or equal to the output f of AB, right? So now an open interval is replaced by a disk, right? A little circle in the XY plane, right? We're just taking these little pieces of our domains around the point that we're calling the XY plane. And as long as you can find one, it doesn't matter how small it is, we can call the thing a local maximum or a local minimum, okay? So let's take a look at some better pictures of this situation. So let me go to a graph. Let's share this one, right? So here's a function, right? I'm just showing you a little piece of it. Notice off, right, in one direction we can see this surface looks as if it's getting very, very high. But right here, let's draw a little bit on this. Right somewhere around here appears to be a local maximum, right? Even though we can find values over here that are much larger, around it, near it, it is the biggest thing going on, right? It's like having the highest point in your neighborhood, right? There might be bigger mountains in the world, but if you want to get a look at your neighborhood, that's the place you go to see the stuff nearby, right? So, for instance, we can put the XY plane into this drawing, right, and maybe make this a little more clear. So, right now it's very clear. There's a disk there, right? You could draw. Let me erase some of this. I can certainly draw a disk in the XY plane, right? If I'm just eyeballing the max. Somewhere down below it, I could certainly draw this disk, right? It can probably get much bigger. We don't run into problems until we get somewhere out here, the points start getting bigger than this point right there. And in fact, if we zoom out just a bit, let's zoom out, right? We see that this function certainly gets much larger than those points. But this point still qualifies as a local maximum, right? Because until we get to this nearly vertical wall, it's the highest point going, right? And again, similar to Calc 1, if this means something to you, right? If this is a function that you're working with that has some real world application, even though this local max isn't the largest, it might be the largest useful maximum because maybe this vertical wall, right? If this has something to do with some kind of chemical reaction, maybe that vertical wall is that reaction cascading out of control, and you obviously don't want to go there. And so maybe you want to maximize your, I don't know, energy output without having this out of control reaction happen. Then this local maximum becomes your spot, right? That's the place where you can get the most energy out, but you're also not, destroying the laboratory you're working in with this cascading chemical reaction. I'm not a chemist. That might be a terrible, highly unrealistic example, but that is that is the notion, right? Sometimes these local maximums are more useful to us, or the other ones just aren't attainable, and so you're looking in the places where you can actually achieve your goals, right? Okay, so there's one example. Let's take a look at another example. Here's a nice surface. It's got these sort of two, almost looks like two paraboloids pointing down, right? Those would both be local mins, right? Now in this case, it's very clear, at least from the part that I have graphed, that there's no points below them anywhere. And so our disk could be an infinite disk, but we don't have to have an infinite disk. We just need to have some kind of a disk, right? So one thing I want to notice with this, I'm going to put in, so I'm going to pick one of these maximums or minimums is at the input 1, 1. So for instance, here's the plane x equals 1, right? Slicing through this surface, right? And we can see the curve of intersection. Let's use red, right? This shape here is like the curve of intersection. And notice, if we forget that we're in 3 dimensions, we can imagine this is the bottom of a minimum for a one variable function. If this is the plane x equals 1, we might imagine looking at the derivative in the y direction, we imagine the rate of change when we change y, the change in z relative to the change in y here is 0, right? If we started over here and we just changed our y variable, remember we're in a plane, x equals 1, so x is not changing in this plane. As we move to what's right on this screen, we're decreasing, 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 then increasing, increasing. At the bottom point there is a point where we would have no change, right? You're going from very little negative change to very little positive change. In the middle, there should be this 0 point, right? And so we anticipate right there that the y derivative, the partial derivative with respect to y, should be 0. Right? Let's look at something in the other direction. Let's look at the plane y equals 1. Right? So now, somewhere about right here, and we see the same kind of shape, right? That we see, if you can see the division between these two, right? There's this curve traced out by the division. And if you imagine now the x partial derivative, you would imagine that there's no change relative to a change in x at this minimum point. In other words, we anticipate that the partial derivative with respect to x should be 0. Right? So let's actually take a look at the partial derivative at this point. This is the point 1, 1, the input 1, 1. It turns out to be 1, 1, negative 1. And let's take a look at the partial derivatives here and see what happens. So let's go back to a whiteboard. All right, second, let's start a new page. Okay, so the function we were just looking at was z is equal to x to the 4th plus y to the 4th minus 4xy plus 1. Okay, so let's take the partial derivatives. In the x direction, we have 4x cubed minus 4y. In the y direction, we have 4y cubed minus 4x. At the point 1, 1, the x derivative is 4 times 1 minus 4 times 1 is 0, and the y derivative is 4 times 1 minus 4 times 1 is also 0. Okay, so as we anticipated, the x and y derivatives there are both 0, and this is not an accident. there's a similar theorem in single variable calculus that I'm going to state for multivariable calculus, which is if f has a local max or min at AB, and the partial derivatives I should say the first order. Let's write this out already. Oh, and I didn't even spell partial correctly. I skipped a letter. And the first order, right, just meaning the first x derivative and the first y partial derivative. The first order partial derivatives exist there. Then the x derivative, the partial derivative with respect to x at the point of 0, and the x derivative with respect to y, the first derivative with respect to y is 0, okay? So, well, let's say a couple things. First of all, we call points with both of these derivatives equal to 0 critical points, similar to critical points in single variable calculus, right? We say points where the derivative is 0 is a critical point, as well as points where in single variable calculus the derivative doesn't exist. We call those critical points. Well, we call them the same thing here. Critical points are where both of our derivatives are 0, both of our first order partial derivatives are 0, or at least one of them doesn't exist, right? And just like in single variable calculus, these critical points are candidates for where we might find a maximum or min. And just like in single variable calculus, they're not always max or mins, right? So in single variable calculus, the classic example is y equals x cubed, then y prime is 3x squared. You get y prime equals 0 at x equals 0, but it's not a max or a minimum, right? Because x cubed looks like this, and so this is just a point where it flattens completely for a moment, but continues going up. And so you can't make any interval around this where all the points are either larger than smaller. They're all smaller on one side and larger on the other. So it's neither a max or a min, okay? We get a similar effect here. So let's go back to this function and do an example to see that now just because we have a critical point, meaning the first order partial derivatives are 0 or don't exist, doesn't always mean we have a maximum or a minimum. So let's find all the critical points for this function that we were just looking at, okay? So I have my two partial derivatives. I have the x derivative is 4x cubed minus 4y. I have the y derivative, 4y cubed minus 4x. So I'm looking for places where these are both 0. In other words, 0 at the same time, right? So I need a coordinate pairs x and y, values of x and y, for which these are both 0. Right? So we have a system of equations. We already solved or eyeballed one solution, 1, 1 worked, right? Let's just solve this. You might be able to eyeball the other solutions, but it's worthwhile to just start to see some of the processes we might use. I have a system of two equations. I can first of all simplify it by dividing everything by 4. So these are equivalent equations. I could quickly solve for y on this side and put this substitute x cubed into this equation over here. So this becomes x cubed minus x equals 0. And this becomes x to the 9th minus x equals 0, or x times x to the 8th minus, oops, that should be a 1, minus 1 is equal to 0. So this gives me x equals 0, or x to the 8th minus 1 equals 0. If we want to, well, we can go through it. It's pretty easy. We get x to the 4th minus 1, x to the 4th plus 1 equal to 0. right? So this is a difference of squares. This one can never be 0, so this has to be x to the 4th minus 1 equals 0, which we can factor again to x squared minus 1, x squared plus 1 equals 0. Again, this one can't be 0 for real numbers, so our only option for this thing being 0 is that x squared minus 1 is equal to 0, which has solutions x plus 1, or has factors x plus 1, x minus 1 equals 0, which gives us x equals 1 and negative 1, right? So you might have eyeballed the solutions, but I just wanted to see a little bit of process. So the story here is that this function has critical points at, let's see, we have, and notice y equals x cubed. So we have 3 solutions. X equals 0, which means y also equals 0. So 0, 0 is a solution. When x equals 1, y equals 1. And when x equals negative 1, y equals negative 1. Right? So I'm being a little bit lazy here, right? We're working in 3 dimensions, but these are our input points. So at these 3 points in the x inputs, we have zeros. Also notice these 2 partial derivatives exist everywhere. There's no numbers we can't cube and multiply and subtract from each other. So there's no critical points due to non-existence, right? So here's our 3 critical numbers. Let's go back to the graph and see a picture of what's happening at these critical points. So let's go back here, turn this guy off. All right, so maybe I'll look from above for a second. Let's get a more familiar orientation. So here I have my x off to the right, y going more or less up, and oops. Why did that just happen? There we go. Okay. So here's the point 1, 1 out here. Here's the point negative 1 out here. And then 0, 0, of course, in the middle. So when we turn the graph this way, notice the points 1, 1 and negative 1 correspond to these very clearly local minimums. But 0, 0 on our graph is this strange point in the middle. And this point is not a local maximum or minimum. So let's try to take a closer look at what's happening at this point. So I'm going to, I hope, make this clearer with adding a couple of planes in here. Here's the plane y equals x. So let's zoom in here for a moment. So I think maybe about right here we have a view. Maybe I'll change this color. Let's make one of these colors a little bolder. I think that helps. Okay. All right. So if you look along the intersection point, or line of intersection between these two, so that's right here, right? Imagine standing. So on this blue axis, that's the point that corresponds to the input 0, 0. If you were standing here and moved along this plane, right, in the direction of this line of intersection, notice you immediately start to slope downward, right, in both directions along this line. I'll change our view. Maybe it'll make it easier to see. All right, so again, imagine standing at that point. You can see 0, 0, 1 is where this plane intersects our surface. If you moved in the direction where the plane is intersecting, notice you move downward. Right, you can kind of see, oh, there's a much easier view of this, right? You're just going to move immediately down these two sides. On the other hand, if you moved in a direction in the plane y equals negative x, you immediately start sloping upwards, right? You're climbing the sides of this hill. So depending on which direction you move, some of the points are above you and some of the points are below you, right? And so it doesn't fall into any category in terms of max or minimums because you're not above or below all the points around you. If I draw any circle in the xy plane, right, the corresponding set of points up here, ones over here are above that point, ones over here are below that point, and so you don't have a maximum or minimum, right? If you take a single step in any direction, you might go up and you might go down, but you're going to do one of those, and so you don't have a max or a min in this case. And for this kind of point, where we don't have a max and a min, we call this a saddle point. Right? So if you do hiking and things like that, you might have been to saddle points. You often have something like, right, where you have a couple of peaks with a ridge connecting them. And if you're standing right on the middle there, if you hike towards one of the peaks, you immediately start climbing. But if you go down the sides of the ridge, you're going down. And so at that point, it's not a maximum or a minimum. It's like the graph of y cubed. It's flat there, but depending on which way you go, you might be going up, you might be going down. Okay? Okay, so let's do one more thing. How do we know when we have one of these without just looking at pictures? So what we're going to do, what I'm going to present without proof is something that takes, at least the way I've seen it developed, is some linear algebra that we don't have yet. So we're just going to use this tool, and further down your mathematical career, you might see a proof of this or be able to come up with a proof on your own. But we're just going to use it because it's an important tool for us to have right now. So this is what's called the second derivative test. Okay, so here's how it goes. Suppose the second partial derivatives, remember there are 4 of them, of f are continuous on a disk with center AB, and the first partial with respect to x at that point is equal to 0, and the first partial with respect to y at that point is equal to 0. So in other words, we have a critical point where the partials, the first order partial derivatives are both equal to 0, and our second order, our second partial derivatives exist. Then we have this test, okay? So first we define, let D, which is D is a thing that changes depending on which point you're at. And the definition of D is you take you're going to take the second xx derivative, right? So you've taken the x derivative of the x derivative, the second order partial derivative xx. Do the same thing with the partial derivative in both times by y. You multiply those numbers together. Then you take the mixed partial squared. Now, notice our second partial derivatives are continuous here, which means that when the second order partial derivatives are continuous, it doesn't matter the order. So it seems like we're missing one of our second order partial derivatives, but really we're taking the product of these two, but since they're the same, we might as well, they just write it this way, right? So it doesn't really, because they're the same, it doesn't really matter. So we compute this thing we call D at this point, and then we have the following. If D is positive and this derivative is also positive, then we have a local min. If D is less than 0 and this derivative is also less than 0, excuse me. Oh, sorry, this part's wrong. Yeah, excuse me, I wrote this wrong. I knew something felt off. My brain couldn't quite communicate that to me. Then we have a local max. And if this D is less than 0, then f of AB is not a max or a minimum. Okay, so this is one of those rare times where I'm just going to let us accept this as a rule, and why it works this way takes quite a bit more work than we're going to do at this point. But let's do an example. Let's go back to this example we've been looking at, where we have z is equal to x to the fourth plus y to the fourth minus 4xy plus 1. All right, so we've already computed z in the x direction is 4x cubed minus 4y. In the y direction, we get 4y cubed minus 4x. Let's take the second partial derivative with respect to x here. We'll get 12x squared. The second partial with respect to y here gives me 12y squared. And let's compute the mixed partials. This is going to be -4. We expect this to be the same, and in fact, it is. And now let's compute d at those 3 points. Well, let's just do one at a time. Sorry, let me do it this way. Remember, our 3 critical points we had just found moments ago were 0, 0, 1, 1, and -1, -1. So let's compute this at 1, 1, right? Well, then we need to look at the value of, we already know that the first partials are 0 here, right? We did that work already. Let's take a look at the value of, at 1, 1, z, this partial derivative is going to be 12. This partial derivative is also going to be 12. And so d at 1, 1 is going to be the product of these two, right? I'm just using the formula over here. I've used z instead of f, but it's the same idea. I'm going to get 12 times 12 minus the product of these two derivatives, the mixed partials, or I can just take one of them and square it, -4 squared. And it's clear, 144, we're going to get -16. It doesn't matter what it is, it's clearly positive. And this derivative at this point is positive, so we have a local min, right? Which we already determined visually. We get the same thing at -1, -1. Notice everything's going to work out the same because this derivative is squared. This derivative has y squared, so even though we're putting in a negative, we get the same numbers. And d at -1, -1 is going to be precisely the same. And so it's also going to be positive. And we already know that this is positive. We also have a local minimum. But now at 0, 0, that weird point in the middle, d of 0, 0, well, zxx is equal to 0, zyy is equal to 0, so d is equal to 0 times 0 minus -4 squared, right? -4 doesn't change because both of these mixed partials are just -4 regardless of what point we're at. And so we get -4 squared is 16, and we're subtracting it as -16, which is less than 0. So we get that it's not a max or min as we expected, right? Because we looked at that picture and saw that that was the case. Okay, so there is our second derivative test when we have functions of several variables, or 2 variables, excuse me. There are more versions of this as you go into more and more variables, but that's going to be it for now. Okay, that's it for this video. We'll talk a little bit in the next one about absolute max and mins. We'll see again some nice parallels to how we deal with absolute max and mins in single variable calculus as we do at this point. Okay, I will see you all in the next meeting. Thanks, everybody.